second topic of our discussion. So as you can see in the literature, what we have given this table where we have composition of gas, that what all gases there in atmosphere: nitrogen, oxygen, argon, carbon dioxide, neon, helium, methane, krypton, nitrous oxide, N2O, hydrogen and ozone. In the second column we have given percentage by volume. All of you know nitrogen is 78%, oxygen is around 20.95% or 21%, argon is 0.95%, and CO2 nowadays can be considered as 0.0380 or 400. Then in the last column we have given these mixing ratios in ppm, which are of importance, especially for CO2, which is nowadays something around 390 ppm or 400. Then average Earth's temperature, all of you know, is around 15 degrees Celsius, or some of the literature consider as 20 degrees Celsius. And if there is no greenhouse gas present in the atmosphere, then the average temperature of the Earth would have been -15 or -20. We also know that the most variable component of our atmosphere is water vapor, both in space and time. So the spatial and temporal variation is maximum for water vapor or OH radical in the atmosphere. Then we have given the table for electromagnetic radiations, in which you can see that we have given the series of these electromagnetic radiations, which varies as like we have the order in which you can see the visible range, which is PAR, photosynthetically active radiation, is from 400 nanometer to 700 nanometer, and the simplest rhyme to remember is the Vibgyor. Then if you talk about the radiations, and if I have an order, like at the topmost I have the cosmic rays, followed by gamma rays, followed by X-ray, followed by ultraviolet, followed by visible, followed by infrared, followed by microwaves, followed by radio waves. If I will go from bottom to top, then the frequency of the radiation increase. And we know the relation energy is equal to Planck's constant into frequency, according to which more the frequency, more the energy. So if we move from bottom to top, then the frequency will increase and energy will increase. On the other hand, if we move from top to bottom, then the wavelength of radiation increase, and according to the relation E is equal to hc by lambda, where lambda is the wavelength and c is the speed of light and h is the Planck constant, then the energy of the radiation is inversely proportional to the wavelength of radiation, and hence more the wavelength of radiation, lesser will be the energy. And hence from this discussion you can say that wavelength of ultraviolet radiation is less than wavelength of violet radiation. On the other hand, the wavelength of infrared radiation is more than the red radiations. Hope the points are clear. Now on the very next page in the literature we have given a diagram which demonstrates that the radiation from the sun is coming. All of us know sun as a black body or as a radiating body having a very high temperature around 6,000 degrees Celsius. So this 6,000 degrees Celsius, then the energy of the sun is very high. It is emitting very high amount of energy, having more frequency and small wavelength. So we call these radiations which are coming from sun as short wavelength radiation. On the other hand, the surface of Earth also emits some of the radiation which are less in energy and hence more in wavelength. We call them as long wavelength radiation, and these radiations are in the range of infrared radiation. So these long wavelength radiation, once they are emitted from the surface of Earth. They goes into atmosphere where they are trapped by the atmospheric greenhouse gases such as CO2, water vapor, N2O, etc. And they can't escape from the Earth's atmosphere. And in the literature we have mentioned that the radiations which are coming from sun, the short wavelength radiations, once they start traveling from sun towards the atmosphere of Earth or the surface of Earth, in between they get reflected, deflected, absorb, scatter, reflect, and some part reach to the Earth's surface. Okay, and it absorbs some portion of the solar radiations also, and this is referred to as greenhouse effect. The gases which get a small amount get reflected, or the radiations which are emitted from the surface of Earth, they are basically trapped by the greenhouse gases in the atmosphere, which do not allow them to go back to the upper layers of atmosphere and cause or maintain the average temperature of Earth. Sometimes the examiners in these exams ask questions like greenhouse effect. The greenhouse gases like CO2, N2O are equivalent to what? So they are equivalent to glass. For a simple example, the CO2 gas can be equivalent to a glass in a greenhouse. Okay. Then there is very important law which is very much helpful in understanding this greenhouse effect, which is called as Wiens Displacement Law. According to Wiens Displacement Law, basically this law is applied on black bodies. Black bodies are what? Black bodies are the body which absorbs all the radiations falling on them as well as emit all the radiations which they absorb, and they radiate all the radiations, and none of the black body is 100% efficient. In Wiens Displacement Law, we basically study the relationship between the energy emitted from a planet or a body or a black body and its surface temperature. So without physically touching that planet or black body, we can have a relationship between the wavelength emitted by that body and the temperature of that body. And the relation is given such that where we take wavelength in micrometer and temperature in Kelvin, then we come across a relationship that wavelength in micrometer is equal to 2897 or 2900 divided by temperature in Kelvin. And in this relationship we can see that wavelength is inversely proportional to temperature. Let us assume an example. If the average temperature of the Earth is taken as 20 degrees Celsius, which is around 293 Kelvin, then if we want to calculate that, what will be the wavelength of radiation emitted by Earth in micrometer? So we will simply using this relationship that wavelength in micrometer is equal to 2897 divided by temperature in Kelvin, and temperature in Kelvin here is 293 Kelvin. Once you will do the calculations, you will get a value near around 10 micrometer or 10,000 nanometer. And this 10,000 nanometer or 10 micrometer is the same radiation which is emitted by the Earth's surface, and it falls in infrared region. So sometimes the examiners ask question that what is the wavelength range or what are the radiation emitted by Earth's surface? So the answer is 10 micrometer or 10,000 nanometer and infrared range. Now we will be coming on a very important concept of lapse rate. All of us know about the environmental lapse rate. So it is nothing, it is the rate of decrease of temperature of atmosphere with increase in height or altitude. Then the next question is, why this decrease? And the logical answers or conclusion which can be given in support of it. First one is that as we move up, the density of the gases with which our atmosphere is made up of decreases. Second, because the effect of long wave radiation of the earth is more near the ground, the same IR radiation which are emitted by the earth's surface, and so as the height increase, the effect of these long wavelength radiation decrease, and hence the temperature also decrease. Now we have shown one diagram where we have shown the altitude on y-axis and temperature on x-axis, where we will be dealing with all the different layers of atmosphere starting from the bottom. First one is troposphere. Then we have a layer above troposphere which is called tropopause. Then stratosphere followed by stratopause. Then mesosphere followed by mesopause. And then exosphere and thermosphere, etc. If we look at this diagram, then you can see that the temperature in troposphere, the maximum temperature is around 15 to 20 degrees Celsius, and the minima after the decrement goes around minus 60, and the height is around 12 kilometers. So if we see this change from 15 degrees Celsius to minus 60, so this change is around 75 degrees Celsius. If we do that final temperature minus initial temperature, it comes out to be around a change of 75 degrees Celsius within an altitude of 12 kilometers. And if we mathematically see lapse rate, it is nothing but dt by dh, the change in temperature divided by change in height. So here we can see the change in temperature is around 75 degrees Celsius and the change in height is around 12 kilometers. So if you will calculate, then the environmental lapse rate will come out to be 6.5 degrees Celsius per kilometer. The minus symbol given here denotes the change or the decrease. Right. Then coming to the tropopause. So this is the layer above troposphere where the temperature remains constant around minus 60. Then above this we have the very important layer called as ozone layer at a distance of 25 to 30 kilometers. Then we have stratosphere, where we have the ozone layer and the temperature goes from minus 60 to 0 degrees Celsius. Above stratosphere we have stratopause. Then we have mesosphere where the temperature goes around minus 110 degrees Celsius and the minimum temperature is observed here. This question have been asked in UGC. Now we will be discussing one by one these layers of atmosphere. First, we will be talking about troposphere. We will be giving some of the key points about the troposphere looking at the diagram given in the literature. So the average height for troposphere is 12 km from the earth, and this height varies at poles and equator differentially. At poles it is around 9 km and at equator it is around 16 km. If we talk about maximum temperature in troposphere, it is around 15 degrees Celsius and the minimum temperature range is around minus 60 degrees Celsius. Normal lapse rate or the environmental lapse rate in troposphere is around 6.5 degrees Celsius per kilometer, or the minus 6.5 degrees Celsius per kilometer. Minus here only denotes the decrease. And why this temperature decrease? The same logic we can give here, therefore, because atmosphere become rarer as the density of the atmospheric gases decrease as the height increase. The second reason, as we have discussed earlier, Earth is always warmer near the surface due to the emission of long wavelength radiation. These are the same 10 micrometer radiation which are emitted by Earth's surface, and more you will move upward, lesser will be the heating effects. Then we talk about troposphere. Troposphere is a very important layer where all the weather phenomena occurs because of presence of hydroxyl radical or water vapor in troposphere. All the weather phenomena takes place in troposphere.